I'm honored to be here today. We present a talk about machine learning's interoperability, and this is our agenda for today. We will, in the beginning, motivate the talk why you would need machine learning framework interoperability, and we do that by introducing an end-to-end pipeline. And having this pipeline, then we can discuss common bottlenecks such as memory management, data conversion, data loading, data transfers. In the end, we wrap up the talk and we give a summary, some take-home message, as well as information for you so you can try this at home. So let's motivate the talk. And on this slide, you see three different professionals. On the very left, a data scientist wearing white scrubs. I know that's not usually what we wear. A CUDA developer with a black shirt. That are the people usually implementing low-level CUDA kernels whenever speed is a matter. And then we often have also data engineers which try to identify new sources of data as well as cleaning the data. And they all might have different preferences for machine learning frameworks. That could be, for example, one of the most popular deep learning frameworks, PyTorch or TensorFlow. Or we could work with tabular data, then rapids might come into play. Numerics data, then we might want to have a look at QPy, that's the green logo in the upper right. But sometimes you would also want to implement a CUDA kernel from within Python. That would be Numba, the framework in the lower left. JIT compilation is also interesting, both in numerics as well as deep learning. And there is a framework proposed by Google called JAX. And this is in particular nice when you need forward mode autodiff or backward mode autodiff. And all these have advantages and disadvantages. And so the different people might choose different frameworks, and our job is to explain how they could interoperate. And let's see on the next slide what is the content of this talk. We will start introducing such an end-to-end pipeline for basically outlier detection of heartbeats. Then we will discuss how data has to be copied in between those frameworks. And on the right, you see a nice overview how this can be done. And we talk about that in detail. Miguel will dive down on memory layouts, memory management, memory pools, data conversion. And in the very end, we will discuss hardware accelerated copying using RDMA to basically avoid the CPU while copying data back and forth. And okay, let's start. Let's have a look at the pipeline. We coded that pipeline in a Jupyter notebook for you, so you can try it at home. On the left, you will see the full pipeline for the hard segmentation, and I will explain it in detail in a sec. We also provide a Jupyter notebook with a conversion table that shows you code snippets, how to convert data from one framework to another efficiently. And let's dive into the end-to-end pipeline. Yeah, this will be a toy model, so not a real application in practice. We are basically going to segment 20 hours of ECG streams of heartbeats, basically continuously measured, and they are stored in CSV format on disk, right? Our job will be to segment them into isolated heartbeats that will be 100,000 K, and then train a variation autoencoder for outlier detection, also for generating new heartbeats. Whenever you have to convince someone that they're still alive, you could generate some heartbeats. Of course, you want to visualize them, and that will also be part of it. On the left side, you see the enumeration of different segments in a heartbeat, usually with letters P, Q, R, S, and T. I will sometimes refer to them, but don't overthink it. And a disclaimer, this is a toy model. Don't diagnose heart diseases with that at home. Leave that to the experts. So let's dive into the first part. Let's keep it real. Most of the time, someone will just enter the room and give you a hard drive with data on it, or point you to some cloud storage with a CSV file. We could argue that there are better formats to store time series, but it's not unusual to get it in CSV. And we would have to parse it. You could use pandas for parsing it, but here we use Rapids QDF, which is a GPU-enabled drop-in replacement for pandas. And many people don't know that's actually quite expensive to parse floating point data stored in ASCII on disk. And therefore, it's a good idea to actually do that on a GPU, and you will end up with a data frame that lives already on the GPU. You can see that on the right on that slide. Okay, we have the data on the GPU and we can pass it at the speed of light. That's great, but now we would like to isolate them. Remember, continuously measured heartbeats. So we need some mechanism to isolate them so we have different heartbeats. We can achieve that with a convolution. Here we choose a global convolution with a wavelet being accelerated by a Fourier transform. You could implement that in NumPy very easily, but again, since we want to be on the GPU for the sake of the huge compute capability and memory bandwidth, we choose QPy, which is a drop-in replacement. And to achieve that, we would have to copy the data from Rapids to QPy. And therefore, here the first problem arises, we need to transfer data. Going on, we would, on the next slide, we can see that we would then want to embed the heartbeats of potentially different length into a data matrix of fixed shape. There is no good convenient tool to do that either in Rapids or QPy, but it's very easy to do that writing a custom kernel, a CUDA kernel in Number, which is basically writing CUDA kernel from within Python. And we will achieve that, and it's actually not hard. You can see it in the notebook. Nevertheless, we have to copy the data again. On the right, you see the embedding. We basically embed each heartbeat in a fixed length vector of 250. We will also normalize it by removing the mean and equalizing the amplitude. Well, and now we have a huge data matrix of 100,000 heartbeats, and we would like to train a variation autoencoder in PyTorch. And this is what we do here. This is a vanilla variation autoencoder as proposed by Kingma in his PhD thesis. It's basically a normal autoencoder with the exception that in the latent space in the middle, you basically enforce that the points are distributed according to a prior probability distribution. In this case, it's a Gaussian. So we're decompressing a heartbeat of length 250 to 2 points in a 2D point in the plane, and you basically see a scatter plot, which are ordered heartbeats. Whenever they are in the middle of the Gaussian, that means they are quite usual or quite common under the training set. And if you find a cross in the outer region, that means that is an unusual heartbeat, probably an outlier. And then you can decode it with the right side of the topology again to be a heartbeat, and this is how it trains. You basically train it for the identity. Again, we need to copy data, and we can finally visualize it using Rapids Q-cross filter. And here we could either take the 2D points in the plane and pass it through the decoder. Or we could even come up with new points that we synthetically put into the plane and sample it. That's what we did on the right, 9 different heartbeats. The coordinates are the coordinates in latent space whenever the numbers are big, so not near the origin. That means this is an unusual heartbeat. For example, the last row in the middle column, this is quite unusual. Good. The conclusion is we have to copy data quite a lot. And this could take a huge amount of time, to be honest. And on the next slide, we see basically different frameworks that could be used to achieve the same. You could decide just to use TensorFlow instead of PyTorch, or you could decide to perform the Fourier transform in NumPy instead of QPy, or use pandas for parsing it. Of course, as an NVIDIA employee, I will tell you the more green you see, the better the pipeline will be in terms of throughput and latency. And on the next slide, we will discuss in detail how you can identify the pipelines. Exactly. Here you see a graph. The nodes in that graph are the boxes, either in green or blue. Whenever it's green, it's in a GPU-accelerated framework, such as TensorFlow, or if it's blue, it's a CPU-based framework, such as Pandas. And the edges in between those nodes, those are the conversion paths, how you could pass data from one framework to another. Whenever it's green, this is a zero copy edge, and that means that we can pass data even without copying. We're basically just forwarding a pointer with some information attached to it, and this is really fast. The fastest way to copy data is not to copy it at all. Whenever it's black, it means we actually have to copy data. And whenever we have to copy data between a blue and a green framework, that means that this has to traverse PCI Express, which is slow compared to, for example, just copying data in GPU memory. Good. And there's not always an edge between all pairs. Sometimes you have to stage memory. For example, when copying data from pandas to number, you would have to introduce an intermediate hop, which would be QDF. And therefore, this is quite a useful illustration. So let's have a look at the next slide. It's actually the introduction for Miguel's part, who will now talk about memory layouts, memory management.
Thank you, Christian, and thank you everyone for joining us today. So I like to create this kind of slides that doesn't say anything, but they say a lot. So you all know the cookie monster, so give me more cookies. And that represents what happens with the libraries we use today with TensorFlow, PyTorch, or whatever. They are really greedy. They want to get as much memory as possible by themselves. Why? Because memory allocations and the allocations is really expensive. So what they think is, okay, I will pre-allocate 90% of the GPU memory available, and I will just manage it internally, but I will pre-allocate it once only. What happens that if you have a complex pipeline as ours or as any other people pipelines, you have two frameworks fighting for the available memory. So that's not good. We need to find a solution for that, a way to share the memory between different frameworks. And that is what it is, a memory manager. So under the umbrella of Rapids, and for those who doesn't know it, Rapids is a drop-in replacement for other libraries such as Pandas, Scikit-learn, NetworkX, and many others. With drop-in replacement, I mean same API, but running everything on GPUs, multiple GPUs, and multiple nodes. So as an example, instead of import pandas as PD, you do import QDF as PD, and you can do the same as you do with pandas, but on a GPU environment, much faster actually. So under that umbrella, we created Rapids Memory Manager, which is just an external allocator, which is a piece of software that you can plug into your software to deal with the memory allocations and the allocations, alongside with other things, like for instance, it lets you do login, double check leaks, limiting the amount of memory per consumer. And the great news is that this is open source, all the code is in GitHub, and it is already integrated by multiple libraries like Xebooks, PyTorch, Numba, CuPy, all Rapids frameworks. So that means that they will all share the same memory. So they don't need to fight for the memory. They will just query us to Rapids Memory Manager the memory they need, and it will be provided to them. And we will have that orchestrator, which is RMM. So a really nice tool. And we keep on adding other libraries integrated on this library. Why are we talking about copying data conversion bottlenecks? So the reality is that when we started dealing with these frameworks, nobody thought about multiple pipelines, interoperability. So what happens? For instance, imagine that you have your data in Parquet format and you want to load it with Spark 2.x, for instance, the previous version, or with Pandas. So Pandas usually deals with the data in a row-wise layout that we will see what's that later. But Parquet organizes the data in columns in the disk. So when you are loading the data, you are not only loading the data, but also transposing it, converting that to a target data layout in memory. And that is very consuming. How much? So around 70% of your computational time is wasted on those kinds of serialization, deserialization, transposing, changing data types. That is really, really inconvenient for our purpose. What happens if we all adopt a standard? In this case, this is Apache Arrow in memory data layout specification. So we just need to pass a pointer to the data to the other library, and they will know how to deal with that. And that is the current approach. Most of the libraries currently implement Apache Arrow columnar layout, and they make use of it. And that makes our interoperability much better. Just very briefly, why columnar data layout? So basically, because most of the operation, not all of them, but most of the operations that we perform with data science benefit of organizing the data in columns instead of rows. Let me give you one example. For instance, we would like to calculate the mean of all the timestamps. This is a row-wise layout, okay? So if we want to calculate the mean, we need to read all the values and then sum them up and divide by the total number of values. So we have multiple memory readings on different memory locations. What happens if you have all the data located in a columnar layout at once? You can read everything at once, calculate the sum and divide, and this is much more efficient. Likewise, if we are filtering by source IP or sorting by user ID. And the second thing is that columnar data layouts deal really well with GPUs. They are like a perfect match. Being fair, CPUs introduce the single instruction multiple data instruction set to also deal with columnar data. So it is a win-win, regardless if you use CPUs or GPU. Organizing your data in columns, it's usually very good for your pipelines. So I mentioned Apache Arrow, and this is one specification we'll use, but there are other alternative specifications which are very compatible between them, like DLPack. DLPack lets you exchange tensors between libraries. So for instance, you have a pandas data frame or a QDF data frame in GPU memory, and I want to convert that to a CuPy array. So I just need to do source to DLPack and then CuPy from DLPack. And they are basically exchanging pointers. The data itself is not converted, it's not moved, and that is really efficient. Now, for instance, if you have an array in CuPy here, and we want to create a torch tensor, we just need to do to DLPack in the source part and from DLPack in the destination part. Really efficient. Zero copy, everything remains in GPU memory. If you are dealing with two GPU-based library, and if you are dealing with CPU-based library, they will remain both in host memory. But there are other approaches. For instance, we have CUDA array interface, that it was one specification we invented a while ago, which is also used, and it's really interesting. And likewise, it maintains the memory organized in a very similar way to DLPack and Apache Arrow. So when you are using a framework that organizes the data in CUDA array interface and you want to pass it to a framework that only accepts DLPack, do not worry about that, because it will be zero copy to. It's only just a couple of headers that will be transformed. How does it work? I'm finishing almost there. Is that, for instance, imagine we have some Python code. This is Number. Okay, Number lets you decorate some Python code, and it will convert this Python code into CUDA code that will run on NVIDIA GPUs in a just-in-time manner. And then we have another function here. This function is dealing with a CuPy array in the arrays, and we are using it as input values for the next functionality. So we just take this input value and pass it as a parameter to the segment kernel that it expected a device in the array. But what happens is that because CuPy and Number both implement under the hood CUDA array interface, I can just pass this object safely to the library, and it is understood. So zero copy again. Very interesting thing. We have 40 standards. Let's create a 15th standard. So that is data API, but the reality is that it is doing really well. It is a consortium of members of the industry. We have people from CuPy, from TensorFlow, from PyTorch, from NVIDIA, for many different players trying to create a standard. And a standard in both the functionality, the nomenclature of the method itself, to name the same functionality in the same way, and also how to organize the data and all the things. It is a really nice approach. It is working. We have already the first version of the specification. And this is the standard until we find another standard, basically. I think that with that, I will pass the ball again to Christian to talk about data loading bottlenecks. Christian, please.
Happy to continue. Yeah, let's discuss a little bit about hardware. On the next slide, you will see the PCI Express topology of a GPU being connected to a PCI Express switch, and we also see an NVMe drive and also the CPU being connected to it. So if we would copy data from the NVMe drive to the GPU, usually we would have to involve the CPU. Basically, what happens is that we stage the data in the RAM of the CPU and then copy it back to the GPU. Interestingly, specifically when you talk about servers with tons of GPUs, like 8 or 16 GPUs, you have a significantly smaller amount of CPUs. Therefore, this might not scale, specifically when you have to copy tons of data. And let's dive into that in detail. On the next slide, for example, we see that we could by introducing RDMA, which with the NVIDIA flavor called GPU Direct Storage, we could communicate between the NVMe drive and the GPU without involving the CPU. And that is basically saving you valuable flops on the CPU side, which makes your application scale. And maybe let's have a look here at a data loader. The Rapids QIO CSV data loader implemented in different ways, and you see the slowest variant is the dark green one at the bottom, which basically does the naive approach, as well as a scalable approach that is the blue one, where the throughput scales almost linearly with the number of GPUs. And now just imagine what happens if you're bound by the CPU. That is the green line. When you increase the number of GPUs, you're basically dividing that throughput by the number of GPUs for each of the GPUs, and that's not what you want. You want this linear scaling, such as in the blue line, and therefore it makes tons of sense to use RDMA capability. Let's maybe have a look at a few more examples. Here we illustrated the naive way, copying data from one GPU to another. I already said it, we would have to involve the CPU, copying it in RAM, then copying back over PCI Express. So we finally end up in the GPU buffer of the second GPU. And this is completely superfluous because they are both attached to the same PCI Express bus. On the next slide, we see we could directly copy it from one GPU to the other, which saves us at least the staging in CPU memory, which is awfully slow. But here we basically have a factor of 2, but it can be much worse. Let's maybe have a look at the next scenario. When we have several GPUs in different servers being interconnected by a network, then in the naive way, we would have to copy data from one GPU to another as follows. Copying it involving the CPU to RAM, then staging it in the driver buffer of the network device, then copying it via the network to the staging buffer of the other network device, then copying it back to the driver buffer of the other server. Exactly now this happens, and then copying it over PCI Express to the other GPU. 5 copy operations, incredibly expensive. When we have NVIDIA networking devices as well as NVIDIA GPUs all connected to the same PCI Express bus, as well as using InfiniBand, we can actually copy it from the left to the right without involving a CPU at all. That's what it is, one copy operation. You just divided the number of copy operations by a factor of 5, which can make a huge impact in your pipeline. Maybe on the next slide, a high-level view of the same scenario. You could even use DPUs instead of normal InfiniBand devices to communicate. Those are basically network devices with an attached CPU on it to accomplish different tasks, such as encryption. And in a multi-tenancy setting, when you want to make sure that nobody can listen to the data being communicated between the servers, you could encrypt it, even fully transparent to application, and allowing this RDMA functionality. And that's a good reason to purchase NVIDIA GPUs and NVIDIA networking devices. Yeah, that's basically what I wanted to show. Let me summarize what we have seen. Different people have different needs and different preferences, and there's a good reason that there are many different frameworks with strengths and weaknesses, and therefore complex workloads might be composed of different frameworks, and the job is to basically reduce the impact of communication. This can be achieved via a zero copy mechanism such as DLPAC or the CUDA array interface. If you can avoid to copy data at all, do it. That's a good idea, and memory management should not be underestimated. Allocating data and deallocating it, it's actually expensive. RDMA features such as GPU direct storage and GPU direct peer-to-peer are really good to avoid meaningless copies. That's all what we wanted to show. We packed all the information into Jupyter notebooks. And if you are a person that likes to read listen to us here, there's a series of blog posts which explains everything in detail, gives you more information. There's a slightly longer talk on it on the GPU Technology Conference, as well as the 2 Jupyter notebooks noted. And as a final comment, if you want to interact with NVIDIA, there are plenty ways how to achieve that. We're very much a developer-focused company. Therefore, it's always good to register on the developer pages. It's basically just leaving us an email. If you're a startup, we have a dedicated program for that called NVIDIA Inception. If you want to learn more about GPUs as well as the frameworks running on it, there's a deep learning institute, either for remote hands-off courses, or you could even book an experienced instructor to come to your company. And of course, we're interfacing also with academia and R&D. On the next slide, there's a little bit more information about the SDKs that we have. Whenever you are in a domain-specific setting, could be quantum computation, so that you actually want to simulate quantum circuits, could be NLP, could be sparse matrix algebra. We have SDKs for that, optimized for you. We have a very strong research organization, NV Research, which is publishing papers. We also put all those findings into webinars and blogs, such as today. And we have developer forums where you can reach out to us. And sometimes, even if you have a very complicated application, it would be a shame that's not running on GPUs. We have hackathons, and we're supporting events such as this one. That's all we wanted to show today. Thank you very much for having us. And if you have questions, we are happy to take them.